Okay, today we will talk about page replacement algorithms, but first let me remind you what we did last time. The CPU generates a logical address, and then our system takes that logical address and translates that into a physical address through a page table, right? So that's what we discussed in the previous chapter. And then in the last lecture, we also discussed virtual memory management. In this case, we don't need to have all the pages in the physical memory. So we don't have a frame for every page. So all the pages are on the disk, and based on the needs, when we have a demand for that page, we were supposed to go and get that page and put it into the physical memory. And how that was working, so when an address is generated, as usual, we go to the page table and look at the entry. If the entry was valid, as before, we will do the address translation. If the entry is invalid, then there will be an interrupt, and the operating system will get into charge and will go to a interrupt handling module, basically a page fault module. And this module, what it does, it simply finds out the page that causes the page fault and gets this page from the disk and copies that page into one of the available frames in the physical memory, assuming that we have an available frame. And then based on that frame number, it updates the page table and says that's the frame number for that page, and now that entry is valid. And then now it restarts the program. So now when the program tries to access that address, it will be a valid entry, and based using this frame number and then the offset number, we can find out the physical address, right? So that's what we discussed last time. So today, with the page replacement algorithms, the question that we are trying to address is this, okay? What happens if there is no frame in the free frame in the system? So there are two options, right? If there's no free frame in the system, then you cannot run the program because you cannot get the instructions into the main memory, etc. So you can terminate the user program, which is not a good solution. The other solution is actually we can swap out an old page because it may not be needed for the anymore, or maybe we don't need it for the current execution. So we can pick one of the old pages that is in the memory and then change it, basically basically remove that entry from the table and then bring a new page, the one that's demanded, that's needed, from disk into the main memory. Okay, so that's what's called a page replacement. And with the page replacement, we will actually complete the separation of the logical memory and the physical memory. So that will complete the picture for us. And also the page replacement allows us to run programs with larger virtual memories. So this way you can write programs that can handle large data sets and things like this on a computer with smaller physical memory. The another advantage of this thing is, even though you may have significant amount of memory, but instead of putting all the logical address space into the physical memory, we can just put a small set of these pages into the physical memory. So this way we can support more programs at the same time, right? So these are the advantages of paging. Anyway, so let's get back to the page replacement again. So basically what we are trying to do is we don't want to allocate too many frames for the for different programs if they don't need to use them, right? So we are trying to find the right balance. We would like to just give enough frames to each program that can do the current executions and current data processing. So basically that's the idea now. To prevent over allocation of memory, we need to modify the page fault service routine and include a page replacement algorithm. So this way, if all the frames are used, if nothing is available, then we can figure out one of the old pages that will not be used anymore and remove that page and put a new page into the system. Okay, so that's called the swapping out an old page and then swap in a new demanded page, basically. But of course, we don't know when we swap out a page, we don't know in the future whether we will need that page or not. So if that page is needed again, so we need to bring that page back into the main memory from the disk. So a page may be brought into the memory several times. So of course, if we can know that in advance, we can prevent it. But since we don't know that thing, we will end up doing that anyway. So here the idea is when we are doing this page replacement, we need to develop some algorithms that can minimize the number of page faults. So we don't want to see too many page faults. If I get a page and if it's going to be used in the future, I should keep that in the main memory and swap out some other pages. Okay, so how can we do this? So that's the goal. We can also include some other improvements. We will not focus on this too much, but one of them is really important to know. Basically, remember in each page table entry we had some control bits. Currently we are talking about valid, invalid, but there's another one is called the dirty bit. So that dirty bit simply says when you get a page into the one of the frames into the physical memory, and if it is just you are reading from that frame, probably nothing is changed, right? A copy of that frame and the copy on the disk is the same. So when you are swapping out that page, you don't need to write that page back into the system. But if this page or that frame contains some data, then maybe you will be updating some of this data, right? So in that case, that page or that frame will be different than the copy on the disk. So in that case, when you are swapping that one out, you have to copy that information back into the system. So by using a dirty bit on each page table entry, you can actually make some efficient decisions. So if the page is never changed, then you don't need to write it back, right? If the page is changed, then you can write it back. So that will give you some improvement basically on page handling or the page fault handling procedure. Okay, why we need paging? Let's look at one example. Okay, so here is the idea. Let's assume that we have two programs with 4 pages. So that's our logical address space, and these are my pages, and this is the logical address space for another process. And assume that in the system we have total 8 frames space, and some part is used for the operating system, so we cannot use it. Then the remaining available frames are this, and we have total 6 frames. So if I would like to run these two programs, program 1 and program 2, on the system, I cannot do it at the same time, right? Because that one requires 4 page, that one requires 4 page. In the old systems, to be able to run this program, I have to put all these pages into some frames, right? So I cannot run that these two programs at the same time. I can only run one of these programs in the system. But given that we have now the virtual memory management, actually we can now run these two programs at the same time. And because of virtual memory management, we don't need to allocate space for all the frames. For example, for this process, maybe we will allocate space for this one, for this one, and for this one. But the M will not be in the main memory, it will be on the disk. So when we need it, we will bring that back into the main memory. Similarly, for this process, maybe this is in the memory. This is not in the physical memory yet. It's on the disk, and when needed, we will bring that into the disk. And this one. So total, we have 6 pages, and all the frames are used. But now, let's say if one of the instructions we are trying to run here wants to load some data from page M, and the page M is not in the physical memory. So to be able to execute that instruction, I need to get that page from hard disk into the physical memory. But now the physical memory is filled up with all the other frames. So the way to do that one, we have to pick one of these guys, right? And let's say randomly, I'm just picking, okay, let's just pick that one. So we can write this one back if it was changed, right? And then now we can bring that page back, and then accordingly we can update the table and say that that's now valid. And then of course, since I'm throwing that one away, right, so this will be invalid. So the operating system will go and make these changes in the page tables, and then we will restart this program. And now when it tries to access some data here, now the page is valid, so we can go ahead and access the information. Okay, so that's why we need to do the page replacements, because we may not have enough space for all the pages that we need. Okay. Basic page replacement algorithm is really simple. The first step, this algorithm or this module needs to find the location of the desired or the demanded page on the disk, and then it needs to check if there is a free frame in the system or not. If there is a free frame, we will just simply use it and we don't need to do any page replacement. But if there is no free frame, so this is basically the previously discussed case, right? If there is no free frame, then we have to use a page replacement algorithm to select a victim frame that's already in the on the physical memory. Okay, and once we pick the victim frame based on some algorithms we will discuss in a second, right, we will swap that out. So now the victim frame will be put back on the disk if it is modified. If it was not modified, we can just simply throw it away because the copy on the disk would be the same as that one anyway. But now let's say it's changed, so we will write that page back into the on the disk. Okay, and then we will bring the new page that is needed and put it here, and accordingly we are going to update the page table. So we are going to invalidate the entry for that page, and then we will validate the frame number for the new page basically. Okay, so we have to update the page table. Here I'm assuming that both pages belong to the same program. If the pages belong to different programs, operating system will be able to update two different page table as well. Okay, so anyway, so for the page replacement algorithm, the bottom line is somehow we will discuss different algorithms. We will select the victim frame and then swap it out, means that write that one back on the disk, and then we will bring the new desired page into the physical memory and update the page table and the frame tables basically, and then we will restart the process. Okay, so it doesn't matter which page or the frame is selected as the victim frame, this algorithm will work fine. So what is the problem here is how you select the victim frame, because that may impact the performance significantly, and that's why researchers are investigating different algorithms, and we will see some of them and try to understand what's the idea behind those algorithms and which one may result in better performance. Okay. Okay, so the whole idea here again, when we are selecting a victim frame, we would like to minimize the page fault. So we would like to come up with some solution that can minimize the page fault rate by running it. Okay, evaluate an algorithm by running it on a particular string of memory references. So that's the model we are going to use to judge different algorithms. So here, let's see, what is this? This one, assuming that these are the page numbers that are going to be generated by the CPU. So at this point, we don't really care the specific instructions, because when that page is used, maybe several addresses within that page will be accessed. But since all these addresses are within the same page and this page is a frame, we don't need to really go and get the page every time. We will only get the page when the page number changes, right? So that's why we can just simply focus on the page number, and that string is called the reference string, which is telling us when we are running the program over time, these are the page numbers that will be needed. Okay, 7, 0, 1, 2, 0, 3, 7. But of course, actually, in reality, we don't know the whole string, right? So we just simply get 1 and then page request, and then the next time 2 comes. We didn't have any idea. But right now, we are just showing the whole string so that we can judge different algorithms and compare how they perform under that given input data basically. Okay, that's the simplest replacement algorithm is known as the first in first out page replacements, and the whole idea here is basically when we get the pages, page 1, page 2, page 3, and when we need to replace one of the pages, we always pick the oldest page that was received, right? So that's like a first in first out queue. So basically, if you think one of the implementation actually we will see, we will maintain a first in first out page buffer here. When we keep using the pages, let's say we are using page 5, page 7, page 3, page 6, page 4, and if I use page 3 again, it is in the system. I don't need to bring it again. If I use the 6 again, I don't need to use it again. But then if I, let's say, if I use 9, okay, now all the pages are being, let's say, used. If I get another page, let's say 1, right? So I don't have any frame for that page. So what will we do? We're gonna remove the earliest or the oldest page from the system. So now we will only have these pages in the system, right? 7, 3, 6, 4, and 1 basically. And then we will keep going like this. So if I need to, the next time, if I need another new page, let's say 10, right? So in this case, now this will be kicked out. So we will have these pages in the system. So basically that's the idea. Why this is a good heuristic? Because the idea was the code used before, the pages that are used before may not be needed anymore because the program is advancing, right? So these pages that are being used are not needed anymore, but that may not be true, right? For example, if you have a loop and maybe these instructions are executed, but then maybe if the loop comes back here, then these instructions are still needed. So it's not always true, but that's a good approximation. And also, let's say maybe an array used earlier may be used again. So for example, let's say maybe you have an array like this, right? Maybe you are using this array, searching, sorting, whatever. Let's say if these are the pages for this array, right? Doesn't mean that we will not need that page again in the future. We may still need it. But that's just a one good approximation, and it's a good simple algorithm to start with. So that's why we are learning that one. The nice thing about this one, it's really easy to implement by using the first in first out buffer mechanisms. It can be also implemented using logical clocks or counters. I will show in a second. Okay, and the problem with that algorithm, as we mentioned, it's very simple. However, it has no performance guarantees. Also, it has something called the Bloody's anomaly. We will discuss that in a second, but simply it says if I give you more frames, because every process will have some number of frames, right? Let's say if I give you 3 frames, how will you perform? If I give you 4 frames, I will expect you to perform better, right? But actually under this algorithm, it may not perform better, as we will see in a second. Okay, so let's start with how that algorithm works. So basically, we are going to assume that these are the page references that are coming from the program. We have to access these pages, and we will assume that we only gave at most 3 frames for that program. So if that program needs more than 3 frames, we will replace some of the pages that are not needed anymore, right? So right now all the frames are empty and available. So when we get the demand for page 7, we don't need to do any page replacement because we have an available page. So we can, let's say, use that, sorry, we have available frame, so we can use that frame. And then when the next time page 0 is needed, I have another available frame, so I can use this one. So the next time when I need 1, then I can use that frame as well. Okay, now here is the trouble, right? So when the 2 comes, we don't have any more available frames. So what I need to do, I need to kick out one of these frames, and the question is which one. So according to the first in first out algorithm, the oldest one, the earliest page needs to be kicked out, and in this case it was this one, right? And then now this will be replaced by 2, and then now we will go with, okay, now the 0 is already here, we don't need to make any changes, so 0 is there. And when the 3 comes in, which one we are gonna remove, right? So we have to keep track of which was the oldest frame and things like that. So when it comes to implementation, we have 2 different ways to do it. One is, I will call it like a clock-based implementation or a counter-based implementation. Here we are assuming that we're going to associate a time, or actually a logical clock or a counter, I'll explain in a second, when that page was brought into the memory, okay? And then basically when we need to make a decision about which page to swap out or kick out from the physical memory, we will look at the oldest page, means the smallest number will tell us which page was the oldest page, okay? And then we can remove that page and replace it with the new page. Okay, so with that algorithm idea, let me just show you how that thing will work one more time. Okay, so assuming that every time when we are accessing a page, we will maintain a global variable. So when we are when we need this algorithm, when we need that page, it will be 1, 2, 3, 4. Every time we can increase that logical clock when we need a new page, basically. Okay, so with that idea, so let's start what happens. So here, when we put 1, we will associate the clock number with this, and we will say, okay, the clock for this one was 1, and then the next time when we get 2, so we have available, when we get page 0, we have available spots, and the clock will be 2 associated with this one. And then when we get 1, still we have available spots, so we will put 1, 2, these are the clock values, and 3 here. Okay, and then the next time when we get the page 2, and we look at which clock value is the smallest for those existing pages, and since this is the minimum, so we will replace that page, basically. So instead of that page, we will put 2, basically. Okay, and for 2 the clock will be, of course, 4. For the previous ones are 2 and 3. And when the page 0 comes in, since it's already in the physical memory, we don't need to do any page replacement, so we will continue. And when we get page 3, we do the same thing, right? We look at the memory and see which one has the smallest clock, and as you see, this one, so we are going to replace that page. So now we got 3 instead of 0, so the 0 is kicked out and 3 came in. And as you see in the next C, the first in first out is not good in this case, because the right after this page we didn't know the feature, right? But now we need the 0, so now 0 is not in the physical memory. So I need to pick the one that was the oldest. So let me just continue with this counters. So it was 4. When we put this one here, it was 6. And when we had this one, 3, right? So when you look at the memory and look at the oldest one, you will see that, okay, so this is the oldest page that needs to be replaced. So now it will get 0 here. And the clock for this one is going to be 7, 6, and 4. And then you can continue in this manner, and that will be the output. So I think that's a good exercise for you guys to continue and figure out how we get the other numbers. Okay, so which one goes here? So when the 4 comes here, I need to replace that one. Okay, just try the remaining ones on your pause the video and try the remaining ones, and you can figure out what are the other page faults, which pages are replaced. But when you do the job, you will see this is the right answer. Okay, so just pause the video and do it yourself, and then compare with this solution. So after that thing, now for that given sequence, we can just simply count the number of page faults with as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we got 12 page faults, and keep this number around, because we are going to compare that one with the other algorithms under the same reference string, basically. Okay, here is another solution which is much easier to implement. It's called the first in first out buffer implementation. In this case, what I will do, because it was very hard to keep track of what was the oldest page, so we can represent it, our state of our frames like this. But the other way to do it also, we can assume that these are not actual frames, these are like first in first out buffer for us. Okay, so I can just maintain a first in first out buffer to show which frame is supposed to be in the main memory. Okay, so in the exams I'm okay with that notation or with that notation, and I usually prefer this one because this is easy to follow, basically. Okay, so let's now do this one and see what happens, basically. Okay, here as I mentioned, this is the first in first out buffer. It doesn't show which frame contains which page. Okay, it's just a data structure. Okay, so now when we get page 7, we will put into frame 0 here, but we will put in the data structure 7 here. And then when we get 0, we will say, okay, 7 is here, 0 is here, and now the additions will be here. Okay, and then when we get to 1, so then we will have 7 here, 0 here, and 1 will go here. So you can think that one is like an first in first out buffer. So that's the head, that's the tail, and then you will keep track of it. Now the tail will point here, and then now here the tail is pointing outside the buffer. So what can we do? right? When the 2 comes in, what can we do? So to keep track of, so that's head, that's the tail, right? So to keep track of this first in first out buffer, I will use the shifting of that data. So basically what we can do, actually in real implementations, you can use circular array implementation to avoid these shifts. But right now, just to make life easier, I will use the shifting. So basically what will happen is this, okay? Okay, so now I will shift this. So basically the top 1 will be removed, right? So 0 will be here, 1 will be here. So now that slot became available, so I can put 2 here. So again, the head is pointing here and tail is pointing here, basically. And now when the 0 comes in, we know that 0 is already in the queue, so we don't really need to make any changes. But when the 3 comes in, we know we don't have space and 3 is not in the data structure, so we have to again kick out 0. So move everything here. So 1 will go here, 2 will go here, and 3 will go here. Okay, and again the head is here, tail is here, and now we need the 0 one more time. So simply we will just kick out 1, okay, and put okay, by the way, here 0 kicked out, 1 is kicked out here, and 2 is now going to be here, 3 is going to be here, and 0 will be here. And the next time when we need the 4, okay, so we will kick out 2, 3 will be here, 0 will be here, and 4 will be the newest element. And then in this manner we can continue, and you will see that now the 3 will be kicked out. So we will have 0 here, 4 here, so they are shifted, right? And then the new element 2 will be here. So again, the head is here, tail is here, basically. Okay, if you continue this way, you will see that we are causing the same page fault. So the 7 was replaced here, 7 was replaced here, 0 was replaced here, 0 was replaced here, 1 is replaced here, 1 is replaced here, right? So the output can be this one. In this case, we are showing which frame contains which page, okay? In this case, these are showing just the data structure, the first in first out buffer. So I'm not actually copying these frames into the other frames, etc. It's just a data structure which is helping me to keep track of which pages need to be in the physical memory and which pages need to be swapped out, basically, okay, according to the first and first out. So either that output or that output will be fine, and I usually prefer that one because it is easy to follow what's going on here. It's very hard to keep track of the counters. Okay, I'll again ask you guys to pause the video and do rest of this exercise, and then you can check your answer with me. Okay, so let me pause my video. Okay, I hope you traced the rest of this and you got the same answer. And basically these two are giving us the same idea and allowing us to find out how many page faults we had. And here again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we got 12 page faults under that algorithm with that string, basically. Okay, so let's also briefly say a few words about something called the Bloody's anomaly. So that's somebody, a guy who found out that problem. So basically, in general, heuristically, let's put this way: if I give you more frames, so instead of, let's say, 3 frames, if I gave you 4 frames, you would expect less number of page faults, right? If I give you 10 page faults, then you will never see any page fault, right? So that makes sense. So in general, that's the behavior of all these algorithms. We are expecting as the number of frames that we gave you increases, then the number of page faults supposed to decrease. But unfortunately, with the first in first out things, sometimes what may happen is, for example, if you do this one carefully, if you have only 1 frame, clearly everything will cause a page fault, so you probably will get that many page faults. If you give 2 frames, probably the same number of things. If you give 3 frames, maybe you will get let's say around that many page faults. But if you give 4 frames under this first in first out, sometimes you may get worse page fault than this case, because it depends on which order these frames are coming, and we didn't know that order, right? But eventually, I mean, we will get better results as we increase the number of frames, but that's just one interesting scenario to see, because that happens under the first in, first out page replacement, while that's not happening in the other algorithms that we will study in a second. Okay, so maybe the next question might be, okay, so what is the best page replacement algorithm? Actually, the optimal page replacement algorithm is just a reference model, because to be able to find the optimal results, we really need to know what is the sequence of page numbers in advance. If I know that's the sequence of the page number in advance, then when we need to make a page replacement, the idea here is, in this case, is just simply says, okay, at any point when you need a page, just look in the feature and see when do you need this the pages that you will kick out, right? And then you can kick out the page that will not be needed for a long time. Okay, so let me give you an example here. So let's say somehow we came into this situation. So right now we have these pages 2, 0, and 1 in these frames, and 0 is in the system, so we don't need to do anything. But when we get to page 3, what we are supposed to do, we are supposed to kick out one of these pages, right? But how are we going to decide which page to replace, or which will be the victim frame, basically? So in this case, for each page, so for example, let's say this frame contains page 2, so let's just look at where the page 2 is needed. So the page 2 is needed after 1, 2, 3 references, right? So the page 0 is needed after 1 iteration or 1 page, and page 1 is needed after 1, 2, 3, 4, 5, 6, 7, 8 pages, right? So according to this algorithm, we are, and heuristically also, you see that we don't need page 1 for a long time, so it makes much more sense to replace page 1 with the new page. So basically what we're going to do is we're going to take this one and replace that one with the page 3. Okay, with that replacement, then our frames will be as shown in this case. So now here, let's assume what happens. So now the page 0, it is in the table, it is in the physical memory, so we don't need to do anything. But when it comes to 4, which page we are going to replace, right? So again, the same thing. For 2, we need it right away. For 0, we need it after 1, 2, 3, and we need 3 after 2 iterations. So clearly 0 is not needed for a longer time, so it makes sense to replace 0 with 4, basically. Okay, and now you can try the other ones. For example, now 2 is already in the physical memory, we don't need to do anything. 3 is in the physical memory, we don't need to do anything, and now you need the 0. Okay, so pause the video and figure out which page needs to be replaced, and then you can check your answer with the ones I will have here, basically. Okay, after carefully inspecting this data, hopefully you also find out that, for example, for this case, when we need a 0, page 2 is needed here, page 4 is not needed at all, and page 3 is needed right away. So it makes sense to replace that page, right? And then in the next iteration, this will be replaced, and then the next iteration, this will be replaced, and we will go like this. And as you see now, the total number of page replacement will be 1, 2, 3, 4, 5. So the same sequence of operation. If I knew what's coming in the feature, right, so I would be able to just achieve the same thing with 5 page fault compared to 12 in the previous case. But there's a significant improvement here, right, because these page faults are really an expensive operation, because it involves operating system go and read something from a disk, and remember, reading things from disk is very time consuming, and we should definitely avoid page fault as much as possible. Okay, so that's a great algorithm, but unfortunately we cannot implement it in practice because we don't know the feature, what page numbers will be needed in the future. So this is just for reference purposes. When we are comparing different algorithms, we can artificially generate this sequence of page numbers, and based on this idea, we can easily compute what's the best under that scenario, and then we can see how the other algorithms will perform under the same sequence of page references, and then we can compare these algorithms. Okay, if I cannot know the feature, can I estimate, can I have some idea about the feature, right? So that's the idea. So with that, people came up with an algorithm called the least recently used. So basically, we will use the most recent past as an approximation of the feature. If I use a page just 1 second ago, it is likely that I will use that page in the next second as well. If I did not use a page for 10 minutes, then it means that in the next cycle, I may not need that page, right? So it's again is a heuristic. It's not guaranteed that you don't need that page, but at least it gives you some idea. So then this algorithm is called the least recently used one, and basically what it does, it is going to select the page that is not used for a long time, basically. Okay, so let's just see an example to better understand what's happening. So let's say somehow we got the pages, we made the replacements, and at this point we have these pages in the frames 2, 0, and 1. And since 0 is in the physical memory, we don't need to replace it. But when it comes to 3, 3 is not in the physical memory, and we don't have enough space, so we need to replace one of these pages with 3, right? So what do? Instead of looking forward, because we're assuming we don't know the feature, but we know the past, right? Because if I keep track of which pages came, I can cut backward and say that, okay, 2 was used 2 seconds ago, 0 is used 1 second ago or 1 page ago, and 1 is used 3 pages ago, right? So in this case, this one was not used for a long time, right? So in this case, this is the page we can pick as a victim and replace that page, basically. Okay, so with that, we can replace that page with this. This will be our pages in the physical memory. And now when we need 0, we don't need to do anything because it's already there. But when we need 4, right? So 0 is okay, but when we need the 4 is not here, so we need to decide which page to replace, right? So in this case, what we can do, same thing, right? We will look backwards. So the 2 is needed that time, used that many seconds ago. 0 was used just in the previous page reference, and 3 was used 2 pages ago, right? So in this case, again, what we are going to do, we will pick the longest one. So we will time, basically. So we will pick 2 and replace that page with 4. Okay, and then now similarly, when we need 2, okay, pause the video here and see if you can generate rest of the page replacement algorithms, basically. Okay, I hope for every page reference you did the same trick and figured out that these are the pages that needs to be replaced. And as you see, in this case, we're now under that algorithm for the same reference string. We have 1, 2, 3, 4, 5, 6, 7, 8. So we got 8 page faults in this case. The optimal was 5. First in first out was 12, and this one is 8. So it's better than first in first out, but it is not as good as optimal one, because the optimal is the best. We cannot really beat that one. Okay. So actually this algorithm, intuitively, if you look backward, it is like an optimal algorithm, and we use this past history as a reference for the feature, and in most cases it's doing well, but of course in certain cases it may make a wrong decision. For example, here we replaced the page 0, but right away we just needed the page 0, so we had to bring it back and things like this, right? So this type of things may happen. However, in general, when you look at larger programs and benchmark programs, it has been shown that this algorithm is doing good. And plus, there's another advantage of this algorithm is if I give you more frames, then you will get definitely less page faults. So we don't have Bloody's anomaly under the LRU algorithm, basically. Okay, so the problem with that solution, it's great, better than the first in first out in most cases. However, it's not easy to implement like an as we did the first and first out, right? So the implementation is a little bit harder here, and now let's discuss that a little bit, and then we will see some more examples. Okay, one, actually we can use the counter-based implementation as we did in the first in first out. So in this case, what will happen, we will increase the counter every time a page is referenced. We are going to associate a counter with each page entry, and when a page needs to be replaced, right, similarly we will find the one that has the smallest time of the value. Basically, for a long time it has not been used, basically. Okay, and of course there are some issues with that one. It will cause some overflows in the counters and things like this. So in the first and first out, it was a little bit easier because we were not updating the counter every time when the page is referenced. In this case, we are updating the counter every time when the page is referenced. Okay, so that's why the counter values here will increase quickly. Okay, the other implementation, instead of a first in first out buffer, we can actually implement that one using a stack implementation, and with a few more operations, like when a page is referenced, and if that page is in the middle of somewhere of the stack, we have to take it out from the stack and push it back onto the stack. And every time when we are about to pick a victim, the one that has not been used for a long time is at the bottom of the stack. At the top of the stack is the most recently used frames, right, will be there. So every time, all you have to just from the stack kick out the one at the bottom of the stack. So now you can easily implement this one, but managing that stack is not easy either, right, because you have to maintain some data structure and update different parameters on that stack, basically. Okay. Yeah, we will talk about that stack implementation on the next example. Okay, and also you need some hardware support to make these things efficiently, because if you try to implement everything about these things on the software, then every page reference will require you to actually also do all these things, which will cause a lot of memory overhead, and it will slow down your programs, right? So definitely some help from hardware will improve the performance. Okay, so let's look at these two algorithms, counter-based algorithm and stack-based implementation, because in the next assignment, second part of the algorithm, you will be asked to implement an LRU algorithm. You can either implement this one or the clock-based one that we are going to discuss in a second. You don't need to implement both, and since we are just learning, I think it might be easier to implement that one than that one, because this one requires to implement the stack data structure. This one just simply associates a counter with each page, and every time you're just searching for the page that has the minimum counter value, right? So it's a little bit easier to implement than this one. Okay, so let's just start. Okay, so basically what we are going to do is every time when we are getting a page, we will have a counter that will be incremented. And as we did in the first and first out, we will basically, when we get a page, let's say page 7, it is available, so we will put page 7 into available frame and put that counter here. The next time when we get page 0, we will put it here with the counter. When we get page 1, we will put it with the counter here. Okay, so the next time when I get page 2, I need to find out which one needs to be replaced. Remember what we said about the counters? We pick the smallest, the page that has not been used for a long time. So we will pick, in this case, this frame and put the 2 here, and the counter is now going to be 4 for that one, 0 is going to be 2, and this will be 1. Okay, so now when the page 0 comes in, so here is one of the difference between LRU and the first in first out. So remember, in the first in first out, when 0 came, we did not change these counters, right? Because we just said it is in the page, so don't do anything, continue. But in this case, since page 0 is just accessed, we will update that counter and make it that one as 5 now, because this is most recently accessed, right? So we will increment that counter. Okay, and then in the next cycle, when I need 3, and then if I need to kick out one of the frames, I will again look at which one has the minimum. In this case, this one has the minimum, so now we are going to pick that one as our victim frame and replace it with 3. Okay, and now the 3 will have, this has the counter 4, this has the counter 5, and the 3 will have the counter 6. And again, when the 0 comes in at time 7, we update that counter, right? Now it becomes 7, and when the 4 comes in, it's not in the physical memory, so we have to pick one of these frames as a victim. In this case, this will be the victim because it has the smallest counter, right? So we will pick that one and put 4 here with counter 8. This one has counter 7, this one has counter 6. And now this 2 comes in. So when the 2 comes in, what I need to do is I need to again look for the frame that has not been used for a while, and it's the one, right, with the smallest counter value. We will pick this one and put 2 here with the counter value 9, and this one has 7, this one has 8. And now when the 3 comes in, same thing, right? So we pick the one with the smallest, we replace that one, so the counter will be 10. This one was 8, this one was 9 as a counter. Okay, so please continue with the rest of this. And so first pause the video for a second and do the rest of them. And then I'll pause my video as well and then finish the job. Okay, here the counter for 0 is 11. 3 was initially 10, and for 2 it was 9. But see, there's an interesting case here. So now after this page is installed, we get 3, but 3 is in the system, but we just update the counter. So now it becomes 12, and then 2 comes in, it is in the system, so we don't need to do any replacement, but we will update the counter, so it will become 3. And then when the 1 comes in, 1 is not in the physical memory, so we will pick the smallest counter, which is this one. So we will kick out this, and we will put 1 here, and then of course 3 here. So let's put 1 will be here with 14, 3 will be here with 12, and 2 will be here with 13. And then again, when this frames in the physical memory, so with the counter 11, counter 12, and counter 13, right? So next comes page 2, and it is in the system, so all we have to just update the counter, so which will be 15. And then comes 0, and it is not in the physical memory, so we have to find the one with the minimum counter, which is sorry, this one was 14. Okay, so this one has the minimum, so we will pick that one as the victim, and we will replace that one. So the counters will be here 14, this one will have 16, this one will have 15 as the counter value. Okay, so then what we are going to do is we will get 1, and 1 is in the system. All we have to just update this, so it will be 17, and 16, 15, good. Then comes 7, and then we pick the one with the minimum counter, which is this one. So we will replace that one with 7, and the value will be 18 here. That one was 16, and this one was 17, right? So the next comes 0, it is there, so we'll just update the counter, it will be 19. Next comes 1, it's in the memory, so we'll just update the counter 20, and we are done. There is no more frames, so we will stop at this point with this algorithm. And these are the page replacements under the LRU, which we discussed in the previous slide as well. Okay, I think this is you guys need to really do this one by yourself as well and try to understand how it works, because in the second part of the assignment you will be implementing this idea when we ask you to implement the LRU page replacement algorithm as part of your assignment. Okay, so now let's look at another way of finding out which pages needs to be replaced. We can use the stack implementation as well. This time, again, this representation will be based on the stack. What's the content of the stack? And you can think that's like the bottom of the stack, and this is like the top of the stack. So as we push, we will push this way. As we will pop, we will pop the one from the so actually we are not going to pop something, we're going to remove it. Okay, so we will remove something from the bottom of the stack, because the least recently used page will be at the bottom of the stack. Okay, so we will push this way, so our stack will grow that way, basically. Okay, so with that understanding, assuming this is not the frames anymore, so this is just a data structure to keep track of which frames needs to be in the memory. With that understanding, let's see how that will work. So right now, the top of the stack will be pointed by this pointer, right? And it's empty. So when we put the 7, we will point here. When next comes 7, so when the 0 comes, we will put it here, and now pointer points here. Next comes 1, so we will have 7, 0, and 1 here. Okay, so now when the 2 comes in, remember this is the top of the stack, so this is the bottom of the stack. Okay, so when the 2 comes in, we need to replace one of the pages, and according to this algorithm, we will basically get the thing from the bottom of the stack and remove it, and then we will shift everything, basically, right? So the 0 will be here, 1 will be here, and 2 will be here, basically. Okay, it looks like the first in, first out implementation we discussed, but there is one difference. I would like to talk about that in a second, basically. Okay, and now what happens here is when the 0 is accessed again. Remember in the previous one, if it was in the memory, we did not change its position in the data structure. But now in the LRU, what we are going to do it is if I access that one, then we will take 0 from the wherever it is in the stack, and then we will shift everything. 1 will be here now, 2 will be here now, and we will push 0 back here. So this way we will know that this is the most recently used frame. That's the goal. So this way, always at the bottom of the stack, we will have the least recently used one, but at the top of the stack, we will always have the most recently used one. Okay, so now the content of the buffer will be something like this. Okay, and now we will have 3, and when the 3 comes in, we don't have space, so we're going to kick out that page. So this is gone, so everything will be shifted. 2 will be here, 0 will be here, and 3 will be here. Okay, so now when the 0 comes one more time, same idea, right? So we will take out, see, that's one of the difference from the first in, first out. In this case, we are going to take 0 out of the stack, so shift everything up to this point. Okay, so 2 will stay here wherever it is, so the 3, because we are removing this one, 3 will be shifted here, and then we will push 0 back into the stack. So 0 will be here, so this way we will know this is the most recently used value page, and this is the least recently used page. And then when the 4 comes in, then now we're going to kick out, by the way, so that's the page thing, right? So we're going to kick out that frame, and basically now what happens here is 3 will be here, 0 will be here, and 4 will be pushed here. Okay, so that's another data structure you can use to show which pages are being replaced and how many pages will be replaced and things like this. So in the exams or in the quizzes, I'm okay with that notation or that notation, but in the assignment, when you're writing the C program, it might be easy to implement that one. So I will ask you guys to consider implementing this one, because this will be easier to implement on C. But when it comes to showing things on the paper, this might be easier to follow for you and for me, because it's very hard to keep track of the counters on the paper. All you have to do here is just manage the stack, and every time when you access a page, take it out of stack and push it back on the stack. Okay, so let's just do one more example here. So when the 2 comes in, so you just simply kick out that page and shift everything. So 0 will be here, 4 will be here, and now you will push 2 here. And when you get the 3, it's not on the stack, so we will replace that page. 4 will be here, 2 will be here, right, and 3 will be here. And the next time when we get 0, so this time we are going to kick out 4. So now 2 will be here, 3 will be here, and 0 will be here again. Okay, and we will continue with this. Okay, so here now what happens is this, right? So when you get after this page request, you will get these things in the stack. When the 3 comes in, remember, we take that one out of the stack and push it back. Okay, so now when I take it out, these things will be shifted up. So 2 is here, 0 will be shifted up, and 3 will be pushed back. And when we get 2, we will take 2 out of the stack and shift everything. So 0 will be here, 3 will be here, and 2 will be pushed back on the stack. Okay, and but we are not doing any page replacement. We are just managing the data structure. Okay, and then when the 1 comes in, so now we're gonna kick out 0, so that page will be removed. So we will have 3 here, 2 here, and 1 will be here. And as you see, actually, if you look at one-to-one corresponding, the content of these frames and the content of that stack contains the same page number. But in this case, we are just showing what page is maintained in this frame 0, frame 1, frame 2. In this case, these are not frames. This is just a data structure showing us which pages are used on in some frames, basically. Okay, so either one is fine with me as long as you are consistently using either that notation or that notation on the quizzes or on the exam. Okay, I'll stop here for a second and let you guys finish the rest of these things, and let me see how you will do. So let me pause and finish the job for you as well. Okay, I hope you worked on the example and you got the same picture as I got here. Finally, the content of my data structure will end up being something like this. Okay, and these are the circled ones are the page fault, and as you see on both pictures, we have the same page faults and we have the same pages in either in the data structure or in the frames. Okay. Okay, from the class web page, please get quiz 10 and work on this one. And when you are doing it, you can either use the cloak or the counter based notation, or the first in, first out buffer, or the stack representation when you are presenting. I would prefer you guys to use these two when you are tracing the LRU and the first in, first out, because it's easy to see, but I'm also okay with the clock-based representation of the buffer. Okay, so that's going to be an assignment for you guys, and we will post that on the Blackboard so you can do your work and scan it and submit it so that we can give you participation credit through the Blackboard. Okay. I would like to also mention 2 issues. I will keep this as optional material, so you really don't need to study this stuff for the exam, but it's a good idea to know. So the LRU approximation algorithm, as we discussed, is very expensive to implement, and it requires a lot of hardware support to be efficient. So to get around this problem, researchers implemented some approximations of these LRU algorithms. One of the ideas here, for example, is called the second chance algorithm. It basically what it does, it is working like a first in, first out, but when it comes to replacing a page, they don't replace the page right away. They just look at the reference bit. If that page was referenced, it means that page was accessed, so they give that page a second chance. But what they do, let's say if that page was used, so they set it to the 0 for this time, so they don't kick out that one and then keep going. So when they find a page which has not been referenced recently, so then they kick out that page. And this way, there was a very simple implementation, and it has been shown that this has significant improvements over the first in, first out, and it somehow approximates the LRU algorithm. Okay, so I just want to mention this one. And also, researchers propose different page replacement algorithms, because depending on your application, some of these generic algorithms may not work well. For example, list frequently used pages can be replaced, more frequently used pages can be replaced. So all these have the same idea. Basically, you have to keep track of which page is least frequently used and which page is most frequently used. Then when it comes to picking a victim, so you can pick your victim based on that idea. Again, these algorithms are fine in the context of very specific applications, and if you know that your program will benefit from most frequently used page replacement algorithms, then you can design your system or configure your system to use that algorithm basically. Okay, there are several other improvements can be done along with the paging to improve the performance. For example, instead of every time when a page fault happened, instead of going and finding a page and then bringing it from the memory, what they do, they reserve some of the a pool of the free frames. So when a request comes in, right away they are able to put one of the frames into you, and then they in the background, the operating system tries to find another frame, and then it swaps that out and gives that frame, puts that frame into the free frame pool. So when there is a demand, right away we can meet that demand, but then behind the scene, operating system can find a victim frame and remove it and put that frame into free frame pool, so that when there's a need, we can quickly meet that demand. So that will increase the response time to the programs, right? Okay. And again, as we mentioned before, when we are swapping out a frame, if it is replaced, if it's changed, it is a good idea to only write those frames back into the memory. Okay. And also there's like sometimes we can mark another improvement is we can mark some frames as free, but instead of kicking them out, clearing their content, we just can keep it. If they are needed, we can just simply recover those frames instead of getting them from the disk again. But if we need a free frame, we can use those frames basically. Right? So these are all really tiny incremental ideas that can give better results in practice basically. Okay. And for some applications, also some operating systems may allow applications to decide which page replacement algorithm to use, etc. So those are also possible solutions, and instead of general purposes, for example, a data management, also for example, a database management system might better know how to deal with the pages and which pages are needed, etc. So the operating system may allow those type of applications to manage the pages by themselves, right? Okay, so with that, I would like to stop here, and the next time we will talk a little bit about performance of demand paging. And that's it for this section.